And with this, I would then like to invite our next two speakers, two other SmartThings ESRs, so Gabriele and Priya, who will be talking about advanced local self-repair. Priya and Gabriele, the floor is yours.
Okay, so thank you, Tim. Yes, so thank you, Tim. Hello, everybody. My name is Gabriele, and today with Priya, we are going to discuss the work of our work package, which, as you can imagine after Claire and Sina's presentation, is work package number 2. Specifically, within the overall SmartThings project, our work is focused on the techniques of advanced local self-repair and the related applications and production processes. Now let me give the floor to Priya, who's going to discuss and briefly introduce the state of the art and the current conditions of the construction environment.
Yes, thank you, Gabriel. In the beginning of this workshop, Neely clearly mentioned how concrete and infrastructure is important for us. From a user point of view, concrete gives us quality life in terms of accessibility and protection through buildings and infrastructural alike. But these marvelous structures look in perfect condition and can perform their intended functions as required throughout its service life. During construction, they are given a certain performance range and also designed for a specific service life. During the service life, an initiation of a damage can occur. And in this current condition, it can be both internally and externally the damages for the different structures based on its environmental conditions. This can be some macro cracks that can compromise the durability functions, as we saw in earlier presentations, and lead to ingress of harmful ions like chlorides and sulfate attack, also induce some stress-induced damages. This occurs in the range from micro scale, where the inevitable heterogeneous nature of the cementitious systems create microcracks in the systems, which, when unattended, can propagate to form macro cracks. And if that is also not controlled, ultimately leads to the damage of the entire structure. It can range from buildings and car parks in a normal environment to very extreme and harsh environments, such as in the case of the marine structures. And thus, in this current damaged situation, when no intervention is done, you can clearly see there's a reduction in the performance and it does not achieve the required service life. In the current practice, we have different repair alternatives where we attempt to increase the performance and also slightly increase the required service life. This particular repair technology can be both structural, like in the case of FRP sheets used for strengthening of structural elements, some corrosion repair techniques in the use of galvanic protection and coatings of the rebars, and more localized repair using repair mortars and epoxy injections for both patchwork as well as for localized damages. However, there is still some challenge that exists in this repair technology. For instance, they are not entirely durable, meaning a repetitive repair is required for the same place and for the same damage scenario, which makes the whole system a bit inefficient in terms of cost and time. It can be alarming to note that per annum, billions of euros is spent only for repair and maintenance. And as also we know, most of the repair technologies use cement-based systems, and cement causes a very big burden on the environment and can be very polluting.
Yes, so these lead us to this comic where actually is quite accurate, where the spending, which is not just related to the infrastructure, but actually to every type of structure system, is extremely expensive. At the same time, quite often, this gets also prohibitive on a practical applicative point of view, so that whenever there is the question, can it be fixed? Well, the answer is, let's see, because most of the times, apart from being extremely expensive, as I just said, is also very complex and sometimes also unfeasible on a practical point of view. So what if there was a system which was durable in terms of the performances that have been designed and that this system, this construction, is supposed to achieve and accomplish on both a structural, but at the same time, a serviceability point of view? At the same time, if we take into account what Claire and Sina have presented before us, the self-healing, there are different self-healing, self-repair methodologies that can be applied and that can be used to accomplish a durable and sustainable system. Moreover, it could be very interesting to achieve and accomplish a self-sensing approach related to the system, where basically different sensors and different techniques and methodologies can allow us to understand how the system is getting damaged, how we can trigger the self-healing or self-repairing responses, and at the same time understanding to what extent these repair processes have been effective and efficient. As Priya has previously presented, at the same time, sustainable concrete is a very strong issue, as she has just said, that cementitious materials such as concrete, mortar, and grout are extremely polluting. Allow me here a brief digression with respect to our current times. We know that recently, several countries in Europe, but actually all over the world, are focusing on recovery funds to trigger the economy back after the strong hit that has suffered after the pandemic. This generally is reflected on the production and construction of many structures of different typologies, clearly. However, this is strongly in disagreement with the carbon neutrality pacts that many countries are committed to achieve by 2050. So what if there was actually a system able to be sustainable and at the same time, why not, even depolluting? Well, if we go back to the graph that Priya was showing us before, and having understood the limits, the current limits of the various repair alternatives that we have right now, achieving using a self-healing, self-repairing system might strongly increase the service life of our system and clearly having a more durable, self-healing, self-sensing, and sustainable material. And this is the SmartThings ambition. Within the 4 work packages where, as the 15 early stage researchers are working on, how to investigate and produce related, for example, to work package 1 on the material point of view, different self-healing, self-repairing methodologies that Claire and Sina have just presented. After that, on the application approach, a practical use of these technologies, of these self-healing technologies applied in the construction field. After that, we will have the work package 3 related to the durability point of view, so on a time scale of the application that has been developed in work package 2. And eventually, work package 4 focuses on the technological transfer, so achieving a commercialization route of these methodologies. And clearly, Priya and I, and as I will explain in the following slide, other 3 early stage researchers belong to the work package number 2, where clearly we're focusing on the application use of the technological methodologies developed in work package 1. Who are we? We're 5 early stage researchers working in 4 different universities in 3 different countries. We're all led by Professor Schlangen from Delft University of Technology. And as you can see, we are formed by Sina, who just presented the previous work package, since, as I will explain later during this presentation, his work is quite essential to both work packages, since he is focusing on the modeling point of view. Then we have Suellen, who's working on an interesting self-healing grout, cementitious grout. Then we have Priya, my co-presenter, who's focusing on self-healing repair mortars, and Sham, who's working and trying to exploit the potentialities of self-healing cover zone of concrete. Finally, there's myself working on the self-sensing point of view application of these self-healing techniques.
Yes. So like Gabriel clearly mentioned, we are 5 different researchers working on different projects, but together we are trying to combine the different technologies that we are trying to develop to form one single multifunctional advanced repair system that we need in this current scenario. This will intend to be durable, self-healing, as well as self-sensing, and of course be optimized so that it can be deployed in the industry and benefits the ultimate goal that the SmartThings works for. To begin with, we have Suellen working on a protective grout. We know that post-tensioning strands in their current scenario undergo corrosion within the strand ducts itself. To prevent this, the protective grout is intended to cover the cables as well as the rebars. In order to achieve this, the use of crystalline admixtures as the core material, as well as layered double hydroxides, which will exchange the harmful chloride ions, will be used. Ultimately, this will result in a non-shrinkable and durable grout system with the benefits of crystalline waterproofing admixture. This grout can also be used in the specific crack closing mechanism in the concrete itself. Like I mentioned, with the addition of layered double hydroxides, a corrosion inhibiting property will be added to prevent the corrosion from happening in the system. Also, a specific type of layered double hydroxide will be investigated with the benefits of a biocide activity, which will absorb the carbon dioxide in the atmosphere and ultimately providing us with a depolluting system. So far, Suellen has successfully developed the grout coating with the required time, such as efflux time, as well as the bleeding property. And also, a very good synthesis of the layered double hydroxide has been commenced in-house itself. In the further upcoming steps, she will be investigating the electrochemical potential as well as the corrosion-resistant properties of this protective grout. Following which, with the grout system in place, we have the concrete cover that protects the substrate as well as the reinforcement. But we all know a poor concrete cover zone will cause a damage to the substrate. And moreover, with the ingress of harmful ions, corrosion can initiate and there can be a loss of structural integrity, which was clearly seen in the earlier presentations. In order to prevent this, Shan, one of our researchers, is working on strain hardening cement composites that will provide an enhanced durability, reduced service life costs, and ultimately protecting the substrate that will give us a negligible effect, not only on the substrate, but also the reinforcement lying underneath it. So far, he has successfully achieved the required strain capacity and a classic reduction of the crack width was achieved. In terms of self-healing, which was autogenous, as you can see from the image, a water tightness recovery was achieved. Looking from a fancy application point of view, he has also developed the mixture to be most compatible in terms of 3D printing. In the upcoming steps, he will be casting more composite systems with the strain hardening systems and investigating for its performance evaluation in real time as well as for its structural performances. More often, the cover zone can also be damaged on a superficial level, and that's where industry uses several types of repair mortars that can be both for a localized damage, just for a patchwork of a physical damage, but also can be for a localized corrosion protection. But the inherent nature of the repair mortar itself, it can undergo two different damage scenarios. One being the debonding from the substrate itself, and the other one, the direct cracking of the repair mortars. Also, a critical challenge with the localized patch repair is that localized corrosion can occur in the adjacent of the reinforcement areas. In order to prevent this, myself will be trying to develop a repair mortar with self-healing capacity with linseed oil macro capsules that can supersede the challenge of debonding and the cracking of the repair mortar itself, and to with the addition of more modified hydrotalicides to make the repair mortar more corrosion resistant. Ultimately, a resilient repair system will also be developed in order to be able to be deployed in terms of spray systems for localized as well as for large scale applications. In the current state, I have successfully studied the compatibility of these microcapsules and for different capsule percentages. An ongoing self-healing study in terms of active crack control and healing observation is commenced. For the specific corrosion study, a systematic procedure will be carried out to measure the chloride penetration depth and the initiation capacity in terms of the performance efficiency of the inhibitors included will be studied. With all the systems in place, we have the self-sensing coating.
Thanks, Priya. So after we have discussed these three layers, it is time now for my research, which is related to sensing coating. Basically, what I'm trying to achieve is the production, construction, and application of indeed a sensing coating, which can be both cement-based, but at the same time also polymer-based, to be applied on top of a substrate which we want to study, which we want to understand its state of damage, for example. So how do we do that? Basically, what we're trying to do is to exploit the properties of different types of carbon nanomaterials. And as you can see here are some of the candidates in order to electrically modify the cementitious-based or polymer-based sensing coating. At the moment, I'm focusing and I'm putting my research on graphene and graphite, but soon I will move towards carbon nanotubes and carbon nanofibers. The idea is to find the optimal type of carbon nanomaterials, as well as the content and different characteristics of such a material. Again, the idea is to, as we know, cementitious materials are electrically non-conductive. So if we apply these carbon nanomaterials and we use that electric properties, we are able to obtain a semi-conductive system. If then we're able to connect these electric properties of just the coating to the state of damage of the substrate, which we want to study, which we want to understand what's going on, well, we will be able to achieve the piezo-resistive effect, also called piezo-resistivity, and therefore having an understanding of the state of stress and/or state of strain of the system. At the same time, in view of a practical application, in view of a practical use, we are trying to understand which methodology might be the best one for an application in the field. For example, apart from the classic casting process, shootability, printability, and sprayability become very interesting options that we are currently investigating to understand which might be the best in the field. Once we have discussed these 4 layers, it is time to move towards the last early stage researchers involved in this work package, which is Sina, who's indeed involved in science-based modeling simulation processes of self-healing, self-repair methodologies. What he's trying to do is basically trying to get an understanding of the physical and chemical processes behind the damage healing cycle and relate them to mathematical equations, to these models, in order to implement them on the computer and produce a finite element modeling process. If we take into account, for example, a self-healing, self-repairing mortar, Sina would try to, using a micromechanical multi-scale approach, would try to get the mechanical properties of such a material and relate it to the amount, for example, of self-healing microcapsules embedded inside. Then he would be able to simulate, to model, and therefore to understand the optimized content of microcapsules in order to achieve a certain mechanical property. The next step would be then to model and simulate the response of the system to healing. So, as you can see, all these 5 different projects can result quite different, but in the end, there is great room for cooperation within the work package number 2. For example, if we take into account the work on concrete cover zone developed by Shan and the mortar, self-healing mortar, who developed by on which Priya is focusing, for example, there is a strong room for collaboration related to the substrate compatibility. At the same time, if we have the grout work that Suellen is scanning, the corrosion resistance is a strong point of connection between Priya and Suellen indeed. Moreover, grout in practice is usually used for several reasons, and quite often the mortar is applied on top of it. Furthermore, if we consider also my project on self-sensing cementitious systems, clearly there is a strong interaction with the 3 researchers on the top, since having an understanding of the efficiency and efficacy of the healing process, while at the same time triggering such a process, become quite interesting and full of opportunities and possibilities. Finally, the modeling developed by Sina would become clearly essential for us, on a hand, to have an understanding and to be able to optimize our mix design, but at the same time to simulate and to know what to expect during the self-healing, self-repair process. To conclude, although we have the 5 different projects and all the 5 of us appear to be at 5 different points, parallel, yes, but independent one another, in the end, all these projects will eventually converge towards the ultimate goal of the work package number 2, which is the production of a multifunctional repair system for advanced local self-repair. So if we can go back to the first comic at the beginning of the presentation, whenever there is this "can it be fixed" question, the actual answer, the actual reply would be yes, it can. Thank you very much for listening to us, and if there are any questions, please be our guests. And if you would like to be updated on it, follow us on the different social media channels.
Thank you.
Thank you.
Thank you, Priya. Thank you, Gabriele. I'm looking now in the chat, and I think that up until now we have not, we are just receiving one question. So is there already an estimate of how the investment costs of self-healing concrete increase compared to normal traditional concrete?
Yes, so there are a couple. Clearly, the self-filling concrete is much more expensive, well, than a normal concrete. However, as there are some estimates at the moment in the literature that allow us to understand that although a higher initial cost, clearly the effects and the, how can I say, the advantages in the long term with respect to the self-healing and with respect to the service life of the system is much higher. So clearly there are, and I'm sure that Vanessa and Davide, who will present after us, they're slightly more related on this topic, might be much better to answer this question.
Yes. And just to add to what Gabriel said, clearly the initial cost is high, but comparing the cost of the repair, where you have to do multiple repairs for the same damage scenarios, the margin is quite large, and hence the additional cost of repair can be drastically reduced, which brings us to the net expenditure to a much comfortable number.
Okay, thank you, Priya. Thank you, Gabriela. I think that was very clear.